welcome to Volumetric locking Q4 noded element, fully integrated. This is the last defect that we can do with this element, and this is a defect that occurs when we have plane strain modeling. So this does not occur for plane stress, because that out of plane, with plane stress, that additional out of plane strain that we have is enough to alleviate the locking behavior. So this is when we have plane strain condition. In the modeling side, this is when we again induce bending. So this is a bending related phenomena, and this happens when as I make the Poisson's ratio approach 0.5 in that plane strain condition, the wheels come off. Okay, if you can go back to the constitutive equation and look at the constitutive matrix and see if you can't evaluate at 0.5 Poisson's ratio, because then you divide by 0. So this is why we let Poisson's ratio approach it. But what you expect is, if you take a material 0.49999 and 0.49999, you add 19 at the end there, that there shouldn't be a big difference in the response or the energies associated with the bending. Okay, what I want to show you is that there's a huge difference between those. So that is purely a locking phenomena. This is a defect of the element that can cause lots of headaches. Okay, why would you want to model material close to 0.5? Well, it's a way to model incompressible materials. So essentially, like trying to mimic the behavior of a rubber-like material. Whatever. After all the deformations happen, when you look at the deformed shape in the linear sense and the small deformation sense, it essentially doesn't change volume. Okay, so that's really what we see there. So let's see what happens. A reminder is that, yeah, we have to make sure that all of these things are met. Q4 element fully integrated, plane strain, okay, bending, Poisson's ratio approach 0.5. This is what needs to happen. Okay, so what I'm going to do is I am going to give you a small experiment. So we're going to be starting off by just showing you that this element, when it comes to plane stress, doesn't have this crazy behavior if I make the Poisson's ratio approach 0.4. There's not a lot of changes in the strain energy. I'm not saying the strain energy is correct, because remember, there's already in the bending, there's already an issue with the Q4 element, that we don't trust the results because there's induced shear there. But on top of that, look at what happens now. Let me show you. So all of this I'm doing here is I'm setting up a small experiment where I can control the material. I can control the material matrix. I can control the stiffness matrix. So I pass the material matrix in from here to set up a small mock geometry of the material, 2x2 square. And then I'm going to complete the eigenvalues, eigenvectors, so that we can choose the deformation mode that we're going to look at and just plot it. This is what I'm going to keep on looking at, this bending mode, just to show to you what happens. So let's run this and see. Now we just need to fish for the right place. I think it's like index 3. Look at that associated strain energy there. So I'm going to plug in this value here. So let me put in 0.4 in here as well. We have that scenario in here. Okay. So there's the strain energy. So it's essentially just over 100,000. Okay. And now I put another 9 in here. I can see it's going up. 115. Okay. Put another 9 in here. So I'm making the Poisson's ratio now approach 0.5. But I mean, again, that the materials are essentially very similar. But what I'm showing you is here that the strain energies just have slight changes in them. They're not going haywire. So that you can see more or less how things converge. So there's that. For that 9 in there. Another 9. That's what we see here. You're starting to get an idea that things are converging to some extent. In that ballpark there, another 9 in there. Things are going up. But again, you can see here, this is really very small changes that we're seeing here. Okay, so things are converging quite nicely if I do the plane stress condition. No problem. Okay, this is not an issue in terms of the behavior we see with Poisson's ratio. This is what we sort of expect. Okay, now I'm going to do exactly the same thing. I'm just going to change from the plane stress to the plane strain. Okay, and again, as a reminder, we divide here by this, so I can't evaluate this term at Poisson's ratio 0.5, because then I'll divide by 0. That is what will happen there. Okay, let's see what happens if I do this. Okay, so there's a deformation mode of, this is now for 0.4. You see it is much larger because it's also plane strain. It's more constrained scenario. So that's for 0.4. Let's ramp it up to 0.49. Just add a 9 in here. Let's fish for that mode, the deformation mode that we were looking for, the bending mode. It's not this. Bending. There's the bending mode. Okay, so you can see there's the bending mode. And essentially this is the, now over 1 million. Okay, add another 9. Now I am at about 11 million. Add another 9. Need to fish for the mode. Fish for the mode. There it is. There's the bending mode that we see. And all I want to show you is, as I put in more and more 9s, every time I put a 9, I go up 1 order in my bending. Look at that. Look at that strain energy. How much that's climbed now. Look at that. Okay. Another 9. Another 9. And I'm going to just at the end show you quickly all the other modes that you can just see. It's the bending mode that's going haywire. Look at that. It's enormous. Okay. Look at that. Every time it adds a digit to the strain energy. So this is not converging. It is crazy. Okay. Although making slight changes to the material. The difference between this and this is very slight. Okay. I expect to see very slight differences, like here. But here I'm seeing enormous differences. That's what's volumetric long. This is why the phenomenon occurs. We don't have to guess of it. We can always go back to our go-to place, look at the eigenvectors and the eigenvalues, interpret them. They will tell you everything you need to know about the element. Okay. So this is really important part of the course. You need to be able to investigate an element. If I give you element stiffness matrix, you need to be able to really critically evaluate what you think is going on with that element. That is an important part of this course. Okay. Because it's the way you inform yourself and make intelligent guesses and have intelligent conversation about what the element is about. Okay. This is just to demonstrate this part of volumetric locking that you can see. So let me quickly show you for this if scenario where I have now. What was the last number of 9s that I had in there? I'm going to just cycle through. Let me just show you this element there. Look at that strain. I'm going to cycle all through all the modes and show you the other modes are fine. Let's start with mode 0. This mode is obviously not fine, but it's not supposed to be fine. Okay, this is the bulk modulus, essentially uniform expansion. There's no Z strain, recall. So this one is supposed to blow up from physics argument, because I'm telling you I'm modeling here a volume preserving material, and I'm clearly changing the volume. Okay, here I expect to see stuff to blow up. Not a problem at all. Okay, so this follows the logic as expected. Because I modeling here the material explicitly as volume preserving with close to a Poisson's ratio of 0.5, and I'm clearly trying to change the volume. There should be large energy associated with that. That's what we see here. Okay, then I go back to the bending mode. The bending is even more than what we saw with the bulk modulus, which is already crazy. But look at this enormous kind of energy associated there with this bending mode. Okay, and I'm just trying to bend this thing, and you can see here by the eye, this area and this area is the same. This is globally volume preserving. Okay, globally it looks like it's volume preserving. Locally it's unfortunately not volume preserving. You can see locally it's not volume preserving because we at the integration points is somewhere here, and at this integration point, what this point is seeing is there's a change in there's a strain in this direction, but there's no strain in this direction. So it sees it as a non-preserving kind of phenomenon. This is why this happens. If you look at the strains that you see at the integration points, the strains say, oh, things are stretching in X, nothing is in Y to compensate, and there's nothing that is happening in Z to compensate. So it thinks it's actually changing volume, and this is why this gets kicked in. It's thinking it's doing this type of thing. It thinks it's kicking in this type of mode. That's why the bending mode, this kind of behavior where you have also not volume preserving stuff. That's why it's having these large strain energies. Okay, just to give you, want to give you intuition behind that as well. If we look at 2, I'm going to just show you that this is also the other bending mode, crazy, and just as insane. But I want to show you the other modes are all fine. Look at those. These values are all nice and moderate. Okay, 140,000. This kind of other shear mode, 140,000. Rigid body mode, 0 strain energy, no problem. Another rigid body mode, rotation, and another rigid body mode. Ugh, what did I do now? Change the factor. Ay. Another rigid body mode, no problem. Okay, this is just to make sure that you have a good understanding of the equation. The eigenvalues and the modes, when you look at them and you interpret the eigenvalue, know that they are relative strain energy, tells you a hell of a lot about what the element is doing. Okay, so this is why it's happening. This is just to demonstrate it, and now let's see it in action. Okay, so here's Q8 element again. Start off with a Q1 by 1 plane strain Q8 model. Again, up to you. Open up those input files, make sure everything's hunky-dory. So let's just show you here. If I do this and I model it, beautiful. Look at that. I'm inducing my my deformed shape. I'm showing you my Vermeer stress value there. I'm showing you my sigma xx value is 120. Remember, there's a sigma zz that is non-zero, that is computed, and so this is what we see. Okay, this is for 0.49. If I do the same with a plane strain simulation, Q4 elements, again 9 of them, 1 by 9, so 1 along the height, 9 along the length. Let's look at what we see here. Sigma YY 120, sigma XX 120, von Mises 59. Okay. Almost no deformation. Look at that. Von Mises 60, sigma XX 120.